Welcome back to Wortheffort Woodworking and the fifth video in our Prerequisite course. Kind of a course that lays out some preliminary information for wannabe woodworkers just getting into the craft so that as you progress on and learn more, the terminology, the theories, that kind of stuff will make sense. So far, we have talked about the material we use, the wood, how it grows, all that kind of stuff, and how we need to adapt to it in order to work with it. We've also talked about the interaction between edges and wood fibers so that the tools we use would make a lot more sense. And we have talked a little bit about how to, sort out what tools to buy and how to get good quality stuff. In the last episode, we began talking about how we join wood together, and that started out with talking about adhesion. This time we're going to continue on that theme and talk about mechanical ways we attach wood together. And that's going to include fasteners and the joinery we use in bench work and furniture making and even timber framing and construction and all that kind of stuff. So come along, let's see how we can put stuff together. Now in the context of this series, in that we're all kind of very beginner level woodworkers, when I'm talking about mechanical fasteners, I'm basically talking about nails and screws. But it's not as simple as just saying nails and screws. There's a lot of complexity and variation in them. I mean, we've been using nails longer than recorded history. The first nails were made of wood. Then we went into the Iron Age, and pretty much we were making and using iron nails all the way up until today. They didn't fall out of favor for more modern day mild steels until the industrial age. Romans used nails all over the place, and in the guilds of Europe, where you went into as an indentured servant or an apprentice to learn a craft, you kind of joined a guild. Well, they had different guilds for woodworking furniture that was done by joinery, dovetails, that kind of stuff, and furniture that was put together with nails, because that was more of a layman style furniture. They were building them faster, quicker, different techniques and different materials. But they had two separate guilds, and heaven forbid a joiner build something that a caseworker was building. I mean, you just did not cross those overs in that guild system. And one of the first jobs apprentices had whenever they were joining these guilds is maybe they were handling the glue pot, like we discussed in the last episode, or straightening nails, because nails were reused over and over and over because they had so much value, because they were all blacksmith made. In fact, it's kind of funny in America, because we didn't have nails were imported from Europe in the very beginning. A lot of times when settlers were moving from location to location, they would literally burn down their house just so that they could collect the nails to take them to the next place to build their new house, because the nails themselves were more valuable than the house. In fact, we refer to nails as like 3 penny, 4 penny, penny being the D designation, because they were so valuable that people used nails as currency. And back when that first referencing came about, it was one of those situations where how many nails could you buy for a penny? If you had a very big nail, you wouldn't be able to buy as many with 1 penny. But if you had a bunch of small nails, you could buy more. And back then, a blacksmith could make an entire lifetime career out of just making pennies. In fact, that's where the surname Naylor came from. It's a very common surname in England and North America. What I find so fascinating is those old blacksmith-made nails. They call them wrought nails nowadays. A lot of times, they are vastly better than the nails we use today. And it all comes back to whether you're using a nail as an edge or a wedge. Now, hopefully you remember back when we did the first episode, we talked about the interaction between edges and wood fibers and how wood was very weak going along the grain, fairly strong going with the grain. And one of the exercises we did was taking a edge, a chisel, and coming towards the end and giving it a good whack. What happened? The wood separated, because at this angle the wood is acting more as a wedge to separate the fibers than an edge. Whereas if I were to take that same chisel, move it cross-section, and start hammering on it, I could hit it as hard as I want, and after a while it stopped going down. If I take the chisel out, you notice no wood came out. But now let's look at the edge. I've severed the fibers on this side, but the fibers on that side were compressed, and they were compressed going down. Well, when a blacksmith made iron nails, they basically started with a square stock of a certain size. So you had this square bar, and then they would pound on the end, and it would come out kind of like that, and then they would hit the top, and that would flatten out the nail like that. But if you looked at that, you're looking at the cross section right now, that looks like a wedge. So if I were to turn this nail sideways, you would still have that right there, but the side angle would look like that. Still that same bar action. It would be just drawn out a little bit to maintain that even thickness going down. So in cross section, it actually turned out that those old nails looked more like your chisel, coming down to a point and then spreading out over there. So imagine how that nail would work if you put it in one direction or the other on a board. Obviously, if you turn the nail sideways, so it was going lengthwise, it would act as a wedge and the board would split. But if you turned it this way, that long portion of the nail would actually sever the fibers and the wedge would crush them, just like it did right here. Now, I want you to think about how it crushed and the action of a nail loosening up. So we have our board right here, and let's just pretend that the grain is running this way. So we took the tree, we're laying on the side. This is going across the grain. So if I take one of these nails and lay it so that the edge is going cross grain, kind of like that right there, well, whenever I drive that nail in, just like when I did the chisel, the fibers aren't flying out. They're being compressed, and they're being compressed in a downward angle. So now I want you to think about what's going to happen if you try to remove that nail. All those fibers are now kind of gripped in at a downward angle, and whenever you pull that nail up, they're going to flex back and they're going to cinch down on that nail, actually making it tighter. So the harder you pull it out, the harder it's going to grip. Is that not ingenious? And that's why you see a lot of nailed furniture from like the 1600s, 1700s, 1800s, 1900s still around and useful today, even though it has no glue in it. It's just the nails holding it together, even in cross-grain situations. I find that just incredible, because modern day nails, they ain't going to do that. Now, some of you smart whippersnappers out there see a flaw in my illustration, in that nobody's just putting a nail into a board. You're nailing one board to another. And this illustration is actually talking about the board underneath you're nailing to. And it only works if that board, you have access to the cross grain. Doesn't work if you're nailing something into ingrain. In fact, nails don't do that much when you nail into an ingrain. Now, all y'all out there that say, hey, wait, Sean, that makes no sense. Our houses, when we build the walls, we have one board sticking up right, we put board on top, and we're nailing into ingrain there. When those situations, nails don't do that much. They're just kind of a temporary clamp until you get the boards on the side of the house, whether it be plywood or battens or anything like that. And those boards you are nailing into the long grain, and those are going to be what grips it and holds it all together. It's not the grain going into the end grain, because going into end grain, no matter what style nail you use, it's acting as a wedge and it's just splitting there. And nails operate via friction. It takes a lot of friction to draw them out. These wrought nails, just also happen to use a little bit of mechanical Velcro edge, for lack of a better term, to hold them in place, whereas our modern nails, well, they're made out of a wire. They're not starting with a bar stock. It's just a simple wire that they grind a tip to one end and smash the other end, and sometimes they will put little rings on the end section right there to hold it a little bit more. But these are made of steel. They're a little bit softer than those old wrought iron ones as far as bendy wide, because they use a mild steel, which doesn't have as much carbon in there. But the only thing that this tool can be is a wedge. Look at that tip. It's pointing at the top and it spreads stuff out. So if I were to come over and using this on the end of a board, we've all seen this happen. You start nailing a board close to the edge, and what happens? The wood splits. Can you see that? It's splitting right there. Right along there, it's starting to split, which means the strength of the cells holding its stuff together is a lot less, so that the friction isn't holding it. That's why a lot of times, see, I can probably pull it out fairly easily right now, simply because there isn't much friction holding it on. And it just basically popped right out. Now, you can turn a tool like this from a wedge to an edge, and this is an old carpenter's trick when you are having to put nails into the end of a board and you don't want it to split, is they will take their hammer and they will blunt the tip. And they actually do make square-headed nails. And now if I drive that in, it's not separating the fibers, it's crushing them down. So there's less stress separating the wood, causing a split. Voila. Now the design of our modern day nails, it has a little bit more to do with production efficiency and cost than it does actual function. These came about, in the turn of the century, the late 19th century, because it's basically a steel wire that they cinch, grind, and then stamp to create the heads, and they make them for different thicknesses. But the variations that they can do revolve around the three main parts. You got the shaft, oh, I forgot what they call that one, the cutting edge, the wedge edge, and the head of it. And as you can see, if you need some holding power, they're going to have a little bit bigger head on them. In fact, something like a drywall nail, they even put an angle on the head right there, so that as it seats, it will bend down a little bit, and then they hollow out the tip right there so that mud can go over it. So this nail right here is actually designed to go below the surface, as is a lot of finish nails, which are used in carpentry and finer work, where they might show. They don't have as thick of a head because they're designed to be pushed down underneath the surface of the wood, whereas these ones that are flat are designed to sit on the surface of the wood, maybe be forced down a little bit, but because they have so much more surface area, you have to take a harder hit to compress that wood to get them to sit level. You will notice also some of them have these little rings on the side, and those are in hopes that they will act like those wrought nails and grip the wood so they're less likely to pull out. Because nails like this, especially in outdoor furniture and stuff like that, just the natural movement of wood compressing and relaxing over the seasons, and the fact that water gets down in there, and if it freezes, it can wedge up a nail in the off season. A lot of times you're having to reseat the nails periodically through the years, because the only thing holding this one in is the friction of the wood. And the problem is, because it splits wood, so you have a nail hole right there, a lot of times you get a split coming down on either side of the nail like that, well, the force is just right here and here. It's not all the way around the nail. There's very little force or friction on the ends. But the thing is, modern day nails, they are cheap. You can use a lot of them in a piece of work. So whereas in the old age you might only use 1 or 2 wrought nails for a given section, you've seen those guys with those nail guns. They'll just put 6 or 7 on a board where maybe 2 would suffice in the old age. So, and you know, you have multiple points of friction, you can increase it that way. Our building methods have compensated somewhat for the lower quality of function of newer nails. Other things you will see a lot of times is if you're in construction age, they will a lot of times coat them with chemicals so that they will last a little bit longer, or they will have an adhesive that will bond the steel to the long grain of the wood. Just something to keep them in the wood because they tend to loosen up over time. Because no matter what you do with a modern day wire nail, it's always going to act like a wedge and not an edge. Screws, on the other hand, kind of combine both aspects of a wedge and an edge. Obviously, if you compare it to a nail, you can see that it has a bit of that wedging action up front, but the threads themselves actually cut into the wood. They separate the fibers out to slice their way in, and that propels the screw down and gives it its holding pressure because fibers are actually in between each one of the threads, which is why screws do not work very well in end grain. We've already established that fibers are very weak going this direction because the wood will split. If all you are doing is separating out these sections right here with those threads as it comes down, well, there's not much holding the wood together on the sides. So if you were to thread a screw into the end grain, what's holding it in is wood that's going to break out very easily. So you can actually pull a screw out fairly easily. Screws work best when they're going across the grain, just as the wood, a nail does. Because if you remember in that test, whenever we put the chisel going sideways, the fibers had to break off. They split off, and that you basically destroy the board pulling a screw out this way as to compare to pulling it out that way, where all you're doing is destroying the wood that's in between the threads. Now, just like nails, really the board that's going through up top isn't too critical. You're actually trying to cinch it to the board underneath. Hence, we have these smooth threads on most wood screws, and that's one way you can tell the difference between wood screws and metal screws and other kinds of screws, is because wood screws designed to go through wood generally have a smooth shank for the distance that the of that top board. For example, this is designed to go through a 2x4, so that's about the distance of a 2x4. If you had threads that came into the top board in addition to the bottom board, what would happen is as it worked its way through, a lot of times, because it takes a while for a screw to start threading its way into a board, well, this top board will start rotting up those threads and you end up getting a gap as it goes through. So if that ever does happen to you, what you do is you back it out until they come together after you've driven the hole, and now it has a hole to start into and it will cinch them down. But ideally what will happen is you'll keep going, and even if they're apart, because this is now smooth right here, there's nothing really gripping it, so it can continue to go down and squeeze those two boards together. So some of the common differences you will see in different types of screws is the space of that shank before the threads start, because they're designed to go through different sized pieces of board. Also, the thread count. You might see screws that have a higher thread count versus a wider thread count. Generally, if you're working in very hard woods, you're going to have a narrower thread count, so it progresses a little bit slower and it's going to get a lot more grip. But if you have a screw designed for softwoods like construction industry pine, generally they have a little bit wider thread count, so not only does it progress quicker for that kind of industry, but the way it grips is designed more for the softwoods than the hardwoods. Now this is a situation where modern day screws, once again, are quite a bit different than what they were making just 50 to 100 years ago. The steel that you find in modern day screws, a lot of times they put nickel coating on them or some kind of coating to protect it, whereas the old ones, they were just good old high carbon steel. And you can tell they rust up a little bit more. This screw right here, with its straight slot, which a lot of people hate, versus one right here, well, I think I paid about $1/4 for one of these. So I get a box that's for $25, $30 of 100, and you can buy a box of these for a couple bucks. It's just different metals. This one can put a lot of pressure on before it starts pulling up. Also notice how it's made. See how the shank, see how the shank is in line with the threads? So this one, the threads are milled out. This one right here, they're stamped out, because you can see the threads actually extend a little bit farther away from the shank because the metal was pressed out, which makes the metal that's holding these on a lot stronger than this right here. Plus the fact that this one right here, I can pre-drill a hole. Now, side note, there is a group of people, I'm going to call them trolls, that are waiting for me to use that term pre-drill, because they're going to go into the comments and say, you can't pre-drill, you can't before drill, either you're drilling or you're not drilling. Well, FYI, the English language does change over time. And when I say pre-drilling, I'm talking about making a hole that the screw will fit into before I screw it into the wood. The pre-drilling defines the order of operation of first making a hole and then putting the screw into that hole, versus just drilling the screw straight in without a hole. It's defining an order of operations, an action within that sequence. So, you know what I'm talking about, so you don't have to go into the comments and make a snarky thing. Well, you're either drilling or you're not drilling. You can't pre-drill. Well, with this vintage style screw, I can pre-drill a hole precisely the size of that shank. And because these were milled out of the same stock, it will slide in that hole and seat itself. And you could even, a lot of people will put wax on these threads, so you can clamp up a carcass, pre-drill all the holes, slide the screws in, even upside down, and because that wax is there, it will stay there. And then using your hand screwdriver, all you have to do is screw it in about that much. You don't have to screw in the entire width. Whereas with these modern day screws, where the threads are higher than the shank, well, you either have to drill a hole that's too big, which defeats the purpose of using the screw, or you drill this screw and you have to screw this entire length of the entire screw down. Granted, nowadays we have those power drills, so it's not that big a deal. Whereas in the old days, yes, they did it by hand, but a lot of times they used a brace and bit to do that one, so it wasn't that much slower. But being able to have the screw stay in the hole while you set everything up, because neither hand would be touching this screw, whereas this design, you have to have one hand on the screw and one hand on your gun to screw it down. This one would stay in your work. So it's a different design that offered more functionality for the way furniture makers were working. So, head designs, you can have a slot that goes all the way through from one side to the other. You can have a cross, which is the same as a slot, except it goes back across both directions. Not as common, because the thing about a slot is if you look at the head design from its side, it comes down straight, and the walls are straight, but so is the bottom. A slot is the same way, just in both directions. Whereas what a lot of people think of when they're thinking the slot is a Phillips head, which is actually a slot, but it doesn't go all the way to the side. And what makes those unique is if you look at the cross section, they kind of come down a little deeper, but there is an angle here to it. And that is the negative aspect of a Phillips head design, is that angle right there allows it to wedge itself out. So if you're not pressing down, it will ride up kind of like a slope. And if you've ever cross-threaded or you kind of work your way out where you destroy the head, that's because, in addition to the poor screwdriver design, which we'll talk about in a second. The other common one you see, especially in North America, because it's pretty much dominant in Canada, is a Robertson one. A square that's in the middle. And it too's design is it has straight down walls. So it won't cam out. Now, if you want a very fun history project, research why one of these is more popular in the United States and one of them is more popular in Canada. It has so little to do with function and more to do with politics. I think it's a fun story if you want to research something. And we also have variations. There's a lot of different styles. More commonly nowadays we're getting into these star ones like the Torxes and stuff like that. And they operate a lot like the Robertsons, but they just have more angles, more surface area, so you can put more pressure on them. The downside of things like Robertsons is all the pressure is like on these corners right here. So if you have a poorly made screw that's a little bit softer in metal, it can kind of bend and eventually turn into a circle right there. Just as bad as these points on the Phillips, they wear out because as you cam them out, it comes up to the point right here where you just knock these off and it turns into a circle and it's all crappy and you hate them. But that very rarely happens on a well-designed slot screw. One reason why people like Robertson and these Torx screws is because the walls are straight, so you can actually get a lot of surface contact area and actually hold the screw up with just friction. Plus the fact that when you're twisting, you're engaging this entire side of the bit so that you can transfer a lot of power to it. The problem with a lot of screws that are poorly made and their mating surface of screwdrivers is not only do we have an angle on the sides so that as you torque out of a screw, you slide out, instead of engaging the full wing of that screw, you're only engaging that corner, and that's why it breaks off. But a lot of them have a taper here so that they will slide in and engage better. So once again, you are only engaging the corners and not the full side. Well, that is one reason why people hate slot screws. It's because the modern day ones are just so poorly made. Look at that screwdriver. A typical, it's a Craftsman screwdriver. I've had it forever. It's a wedge. So whenever I put that in there, it's not engaging the full slot. It's not engaging the full slot of the screw. All it's engaging are these wings right here. So not only does it push its wedge out, but you bend up these wings because so much force is on them. What you need is a square screwdriver that fits perfectly in there. But the thing is, to make one such as that takes money. So this screwdriver right here is a gunsmith screw, and notice it is square on the very bottom. Let's see if I can see that one. They've actually machined the edges. And guess what? Different size screwdrivers are designed to work with different size screws. So it will perfectly fit in there. And sometimes you even have to press it in there to get it to fit just right, because there's a little wire burr on the screw itself. And just like the Robertsons, they will hold themselves up because you have such a tight fit between the screw and the screwdriver. That's why a good screw will cost you $0.25 versus, a few pennies when you buy them by the box. And it's one last thing I want to kind of drive home. If you're buying screws by the box from a big box store, understand those are being made as quickly as possible. A good screw like this vintage one that I spend so much money on, well, they go through the process of heat treating them properly. Where a lot of times if you're buying them by the baggie or the box at the big box stores, they're just heat treating them once, getting them really hard. And if you're using something like a drywall screw, which they are just making as quickly, as cheaply as possible, there's a reason why they break so often. Not only is the design of the head as it goes through, as it sinks itself down, designed to go into a softer material, drywall, than wood. So a lot of times when you get them down to that very little bit, they'll break off at that point because there's so much torque on that screw that's not designed for. It's not designed for as hard of material as wood. So the poorly hardened steel just cracks on you. You do have to seek out specialty locations to buy either these vintage style screws that are just better made metallurgy wise, design wise, or go to a specialty house like Fastenal or stuff like that and ask for good quality screws. They'll know what you're talking about. They'll give you the ones that have good metallurgy, the ones that have good head designs. Just talk to them, ask them if you are just starting out in the craft and you don't quite know yet. Now, mechanical joinery is not just screws and nails and that kind of stuff. The entire kind of subject matter of joinery, woodworking, is developing mechanical bonds between two boards. My workbench, it's a mechanical joint. I have a mortise and tenon. The mortise is in the bench top. The tenon rises up into the mortise. Now, if it just had that, you could lift off the bench top. But by driving two pegs, or shall we call them wooden nails, through there and just putting the slightest amount of glue on the pegs, or in the old days what they would do is they would make a square peg and force it into a round hole. It would start out round and then would end up square. They'd just take it and whittle it down. Well, that square peg would kind of bite in, so it would seat itself and it would never come out. A little bit of glue is just there to create the pegs, make the pegs not want to come out. So without glue on the mortise and tenon, this leg is never coming apart. I will have to cut this thing apart in order to join it. That's why the legs don't fall out. A dovetail joint, like on this case where I'm trying to join one board up here to this one right here, the reason why you put the tails on the side is because the wedging action right here prevents this board from falling down. So the gravity is pulling it down and keeping the joint together. What isn't happening right here is force coming out this way. Now, modern day words, we put a little bit of glue right there because you got long grain, and that keeps this moving out. Because this force, it doesn't take much to keep this board in. But in the old days, when they didn't have glue, they could do the same exact joint, but then drive a peg in, even the size of a toothpick, through that front and the back right there, and that would prevent that board from coming out. Same with sides. You could build an entire drawer with no glue whatsoever, and it would never be able to come apart if you simply put a cross pin coming in here, because that pin would prevent this board from sliding this way. The dovetails prevent it from sliding that way. Same is true for these shelves. You notice I cut them in so that they're now resting on that piece right there. So you don't really need any glue whatsoever to keep that shelf in there, because all its force is coming down into that, and a simple peg from this side through there, about that far, prevents the shelf from coming back this way. So the joinery is a mechanical lock. That's what we're trying to accomplish with all this. And what I just showed you there with those shelves sitting in a dado is kind of a foundation for an entire class of woodworking that combined the mechanical joinery of cutting the wood with the added advantage of using things like pegs, nails, and modern day screws to complement it. So these aren't working that hard. The majority of the labor against gravity is done with the cutting of the wood. And in that, you can have shelving coming in the middle of a board by cutting what they call a dado. That's a recess through going across the grain, typically used with shelvings. Or you could do a groove, which is a recess coming right through the middle of the board. That'd be like the back of panels that could slot in there, and with a little adhesive or pegs, it will stay right in there. Then you have rabbets or rebates if you come from other better speaking countries, and that's either a dado or groove on the side of a board. We just call them rabbets right there, and that is parts that could actually slide into those dados or grooves. And then you just add your nails or pegs or a little bit of glue. Well, I hope you enjoyed that quick discussion on the mechanical ways we put wood together. Now, I will tell you, we just touched the surface. This is just the basic stuff that you would use in like a sophomore level class to actually do the work. We're just lightly dabbling on it. If you really want to have some fun, go to IKEA and just browse how they do their assembly work, because they don't like to send people home with a bottle of glue. They want everything to be able to put together with mechanical fasteners, and they're one of the few companies out there that are inventing new mechanical fasteners for people to use. I think it's kind of cool how they came out with a sliding mortise and tenon finger joint combination. Sometimes it's just fun to go explore, even though I don't really like the quality of their furniture, but how they put it together is fun. And as far as the woodworking as joinery, that's an entire course that we will be covering in the future. I just wanted to give you a taste that there's a reason why we prefer using some joints for different aspects. It just takes a little bit of knowledge and learning how to simply follow a line with a saw, and you can accomplish all of that in the future. I hope you enjoyed this. Remember, be safe, have fun, and that it is always worth the effort to learn, create, and share with others.